So you may well want to know, why does this turn into this when you heat it? Well, the process starts when you give this lattice more thermal energy. You see, that thermal energy to these particles is used for the vibration of those particles around a fixed point. And what you can see is that any part of this structure is capable of a small amount of vibration, but that the particles always go back to their original places. This is true for a solid. In a liquid, they never necessarily return to where they were. They have the freedom to change positions at will. So what has caused this change? What has caused it to go from the atoms being fixed relative to each other to being able to move relative to each other? Well, that thing is the internal energy that this substance has gained. I have a very curious experiment to show you. This device simulates what is going on for our atoms. What it is a device that can shake these ball bearings at any speed or frequency that I like. And what I'm going to do is I'm going to shake them at a high speed, and then I'm going to turn the amount of energy that is going into the structure up. Now look at it. You can see that these atoms are basically staying in their fixed positions relative to each other. They are always returning to where they should be. If I increase the amount of energy going in, and this would be in the form of thermal energy, then eventually you'll start to have those atoms skipping and moving around. This represents a liquid. If I put more thermal energy in yet, it will start to represent a gas. And you can now see that it is basically boiling, and the particles are much further apart. So in a solid, if we increase the internal energy, the particles vibrate more. But why do they always return to their original place? It's to do with these, the chemical bonds that hold them in position. On this model, they're springs, but in real life, each of these atoms' nucleus contains a positive charge that is attracted towards negative charges. The electrons of the adjacent atom is so attractive to this atom that that attraction is like a rope holding them together, or in this case, a spring. Now, if you put some energy in, then you can make this move around on the spot more and more and more until eventually you've given it enough energy to break that spring, to break the chemical bond, and as my poor old model will tell you, to then escape. Have you ever really looked at the mercury in a thermometer? You see, mercury is the only metal that is liquid at room temperature, and yet it behaves rather oddly. What I've got here is a microscope, and we're going to have a look at the surface of the mercury in this thermometer. What we can see of the top of the mercury there is that it forms this rounded bulbous shape. And what causes this is the fact that the bonds between each individual mercury atom in the liquid are stronger than the bonds between the mercury and the walls of the thermometer. It basically means that the mercury prefers to bond with other liquid mercury than it does with the walls, and so it's almost shying away from the walls. When we look at water, we actually see the opposite effect. In fact, water, when you look at the edge, you can actually see it's the other way round. That rather forming a dome in the middle, it's actually trying to climb the walls. It appears that with water, the forces between water molecules are slightly less than the forces between the molecules and the plastic container. And this is what causes the downward curvature of the meniscus. So with the liquid mercury, what we found is that the meniscus was this shaped because the bonds between the mercury atoms was stronger than the bonds that it tried to form in the walls of the container. And so therefore it all tried to get into a huddle in the middle and not try to touch the container wall. Whereas with liquid water, there are bonds there, but those bonds are weaker than the bonds that it can form with the container wall. And so the meniscus goes the other way. But whether mercury or liquid water, this is both evidence that bonds do exist between the water molecules, but that those bonds are not permanent features. Those bonds are much weaker than the bonds that form in a solid, and they temporarily form from this molecule to that molecule to this molecule, and that this is what is overcome when liquid is given some more internal energy. So as I boil this kettle, thermal energy is going into the water because of an energy transfer between the heating element. The electrical energy is transferring into thermal energy. And what it's doing is it's giving that energy to the liquid inside. But all of the particles are moving more and more and more. They're still attracted to each other. What starts to happen is that some of them get given enough energy to escape. There, the hot steam coming out of the top of the kettle, evidence that some of those water molecules were given enough energy for them to escape the surface and become a gas.